Good afternoon, everyone. Well, just wait for 2 minutes for others to join. After that, we'll start the lecture. Are you able to hear me clearly? Are you able to hear me clearly? And the board is also clear. I'm audible or my voice is low? Okay. We'll just wait for 2 minutes. After that, we'll start. We're going to start with new chapter today. In the last class, I said we are going to start with a very important chapter. We'll wait another 1 minute and then we'll start with the lecture. Tell others also to please join the lecture. Missing mathematics lecture will become then it will become very difficult to clear them. Okay, then we will not waste much of the time. It's already 2:05. So let's start with the lecture. So today we are going to start with very important chapter called as matrices and determinants. This is important from your board exam point of view. It is also important from your JEE point of view. And not only that, it is also important from your future point of view also. Okay, and understanding only numericals or solving only numericals, okay, should not be the aim. You also have to understand a little bit of what is happening in the background. That also. Why? Because you go to any engineering, so you have taken math. It means you are going to go into engineering. It can be any of the engineering. So, be it okay, automobile, aerospace, civil, mechanical, electrical, electronics, marine, or any kind of engineering, okay, you are going to deal with two kinds of softwares. One are called as designing softwares, and others are called as analysis software. So, what are designing softwares? You must have heard the heard the softwares called as AutoCAD, CATIA, ProE, SolidWorks, okay, Fusion 360. All these are nothing but designing softwares where you can design the machine parts, so you can design the entire building, you can design the structures, you can design, okay, a car or an aeroplane or something. And then next is an analysis software. So you must have heard the name of the software called as ANSYS, MATLAB, and in other cases, one more also called as Nastran, if you must have heard. But ANSYS and MATLAB, these are very famous analysis software. Why am I telling this? Because in the background of any of these softwares, the calculation is done entirely by this called as matrices and determinants. And if you are going for CS engineering, okay, computer science or information technology, this becomes very important part, okay, which is also called as linear algebra. So maximum portion of your mathematics will be about linear algebra if you are taking CS or IT. You do understand. I'm just giving you the background how important this chapter is, not only from your board exam point of view or JW or NEET point of view, but also from the engineering point of view. You're going to study the similar chapter in the engineering at the same time. All the softwares on which nowadays entire thing works. Okay. Now in today's technology, we don't build the models first. First, we create a mathematical model. That is, we create a model in the softwares, we test those models in the softwares, then we make a model of it, after which the testing is done on the model, and after that, a final okay prototype is created. This is the methodology. So, Every time you have to create a mathematical model, and without this mathematics you cannot create it. So understanding this chapter is very important. Okay, and it is for a good amount of marks in your GWE also. Minimum two questions will be there from this. Minimum two questions I am saying. Okay, there will be minimum of two questions from this particular chapter. Minimum. Now let's start. And today's lecture is the most important, I'm telling you, because I'm going to give you introduction of this chapter, and you have to understand it very carefully. If you're not understanding at any point, okay, please unmute yourself and ask me. Okay. First, second is this introduction. In this introduction, I am going to actually, okay, I am going to actually show you a lot of things which we are going to do later on in the chapter. Okay, which we are going to do later on in the chapter. And that time, if you are not understanding or why this was done, how is it possible to do all these things, so then you can remember the background was today's lecture. So without wasting time, let us start with the today's lecture. And I'm writing two equations. So one equation is 3a plus b is equals to 8. And one more equation I'm taking is a minus 2b is equal to 5. Okay? And what I'm going to do is, first I'm going to solve it by a 10th standard method which you already know. And then I'm going to convert this into something different, completely different algebra. So let's start. So how you will solve this is you will multiply it by 2 and then you can add this equation. So then 2b gets cancelled and you will get the answer of a. Then that value of a you will put in one of the two equations and you will be able to solve. So let's do that. You already know how to solve it. So I'm multiplying equation 1 with 2. Okay. So I'll get 6a plus 2b is equals to 16. Let me give this as equation number 3. Okay. And then I'll add both the equations. So I'm adding equation number 2 with equation number 3. So I'll get a minus 2b is equals to 5 and 6a plus 2b is equals to 8. So, sorry, 16. So this 2b gets cancelled. So here I get 7a is equals to 16 plus 5. So that is going to be 21. So I get a is equals to 3. Let me give this as equation number 4. Now I'll substitute this value in any of this equation and we are going to get value of b. So let me substitute this value in any of this equation. Suppose I am substituting over here. So I'll get 3 minus 2b is equals to 5. Okay. So I'll get 3 minus 5 is equals to 2b. That is, I'll get minus 2 is equals to 2b. Let me give this as equation number 5. And from here I'll get b is equals to minus 1. You already know this method. This you have studied as simultaneous equations. Or linear equations in two variables. Okay, now why do we call it a linear equation? Because you take any of this equation where the degree is 1 and plot a graph, you will always get a straight line. And since you will always get a straight line, therefore this equation of degree 1 is called as a linear equation. Okay, now suppose now instead of A and B, if I would have taken X and Y, or I would have taken P and Q, I would have taken L and M, would the answer change? No, the answer is not going to change, right? Instead of A and B, you write L and M, or instead of A and B, you write X and Y, or instead of A and B, you write P and Q. The answer will remain same. That is 3 and minus 1. So what we understand one thing is, it is independent of the coefficients. The answer which I am getting A is equal to 3 and B is equal to minus 1. It is independent of this A and B. Okay, it only depends on the numbers which are associated. So what I am doing is I am only writing the numbers. So this is 3, here the coefficient is 1, here it is 1, minus 2, here I have 8, and here I have 5. But we very well know that these numbers and these numbers are not fixed. Why? Because these numbers are coefficients of A and B, whereas these are constants. So let me say, denote this by say hash. And if we see, all this 1 and minus 2 are coefficients of B, and 3 and 1 those are coefficients of A. So now what I do is, to differentiate these two numbers are different, I'll put a line in between them. Just to differentiate that, the board is not clear. Okay, just a minute then, just a minute. Give me a minute. Now is the board clear? Now is the board clear or it's still blur? Okay, it's clear, right? Okay. Okay, just to differentiate that this set of numbers are different from this set of numbers. Next, these numbers are belonging to something, right? So just to indicate that these numbers are belonging to something, what I'm doing over here is, sorry. That though these numbers are different from these numbers, but all these numbers are together belonging to some similar thing which are nothing but set of two equations. Okay, and to show that I am showing it by two square brackets, and this is what we call it as matrix. So this is what I call it as a matrix. So now we are going to study. So what we did over here also, we are going to develop a new algebra. Okay, which is only considering numbers. So you can see here I have only written numbers. So only on the basis of numbers, okay, only on the basis of the numbers we are going to solve this. We are going to develop a new algebra. And now, initially you may feel that this algebra is maybe a little bit complex. This simultaneous equation method was only good, but later on you'll realize that this is much more sophisticated, much more powerful, okay, and much more condensed and compact, and very much errorless, error free. Okay, I'll also show you why I'm saying that it is very much error free. Okay, so let's see. Now I want to solve this. What I had done over here, if you just remember, I had multiplied this equation, okay, with 2. Now if you see, this is your equation 1, and this is your exactly equation 2. Okay, here also 1 minus 2, 5, the same thing. These are all the numbers representing A, these are all the numbers representing B, and these are simply constants. Okay. And if you see, you can see the numbers are arranged in the rows, or you can also say the numbers are arranged in the columns. So this arrangement of the numbers in the rows or the columns is called as matrix. So matrix is nothing but the arrangement of the numbers in the rows and the columns. So this is my first row and this is my second row. And therefore I am writing here as R1 indicating the first row. I am writing here R2 indicating second row. So now let me, if I want the 0 over here, if I want the 0 over here, what I can do is, or if I want the 0 over here, in any case. So if I multiply it by 2, okay, and then add it, it will become 0. So that is what I'm going to do. So I'm going to write, I'm multiplying R1 by 2, and this I'm going to add in R2. Okay, this is what I'm writing. Or afterwards I'll make condensed. Just let me only write this 2R1. So if I multiply, the entire row will get multiplied. So this will become 6, this will become 2, and this will become 16. 1 minus 2, 5. Now let me add both of this. So this is my R1, this is my R2. So I can write, okay, R2 plus R1, which means what I'm doing, I'm adding R1 in R2. I'm adding R1 in R2. So this is 6, 2, and this is 16. And I'm adding this R1 in R2. So 1 plus 6, that is 7, minus 2 plus 2, that is 0. And 5 plus 16, that is 21. Okay. Now let me divide this by 3. Okay. So I am writing 1 by 3 into R2. This is my second row. So I'll get 6, 2, this is 16. Or instead, let me divide it by 7. Okay, let me divide it by 7. So 7, 1, this will become 1. 0 upon anything is 0, and this will become 3. So if you see, this is exactly my equation number 3 over here. If you observe over here, this is exactly my equation number 4, which I have written over here. And now if you see over here, these are all of them are of A. This all second column is indicating B, and all this third column is indicating the numbers. So I'm getting A is equals to 3 over here. So I got A is equal to 3. So we are exactly doing similar things what we had already done over here, but here we are just doing in some different way. Now, what we had done is we had substituted this value of A in one of the equations, and we had got the answer of B also. So some similar kind of thing we can try over here. Okay, some similar kind of thing I can try over here. I've already got the value of A. I want to get the value of B. So I can make this as 0. How I can make this as 0? I can multiply it by 6, and then I can subtract it from here. If I multiply it by 6, okay, and then I subtract it, then this will become 0 and only this will remain. Right? So what I'm going to do is, I'm going to multiply my second row with 6. So I'll get 6 to 16, and here I'll get 6, 0. Here I'll get 18. Now what I'll do is I'm going to subtract my R2 from R1. I'm going to subtract my second row from my first row. Okay. So 6 minus 6, this will become 0. Okay. 6 minus 6, 0. 2 minus 0, that is 2, and 16 minus 18, that will be minus 2. Okay, so if you see here, this is exactly my equation number 5. You can see here, equation number 5, minus 2 is equal to 2b. So these were all the a's, these were all the b's, and these were all the constants. So I'm getting here 2b is equal to minus 2. The same thing I had got exactly over here. And from here, I can get my b is equal to minus 2. So now I have got the similar results, but I have applied some different kind of methodology. So you must be thinking, sir, it looks very complex. This is very easy method. Why are we even doing this method? I'll show you that it was only for the first time, and I wanted to explain that whatever you have done, each and every step is over here. Okay, all the equations 1, 2, 3, 4, 5. So all these 1, 2, 3, 4, 5 equations are over here. At the same time, whatever values we had got, that values are also here to show that, and this is for the first time, and that is why I have solved this entire thing. But I'll just show you. This will happen very quickly. In 2 steps, you will get the answer. You can get answer in 2 steps. Okay. So what I had done was I had multiplied by 2, then I had added, and then I had divided by 7. So all these things I can write in one step itself. I can write something like this. Okay. Twice of R1 plus R2. So in first step itself, what I'm doing is twice of R1 plus R2. So I'll multiply it by 2, and then I will add R2 in it. So this will remain as it is, 1 minus 2 and 5. I'm multiplying it by 2, and then I'm adding. So 6 plus 1, that will become 7, and 2 minus 2, this will become 0, and 16 plus 5, this will become 21. So in the first step itself, I've got a is equals to 3. Okay, in one step itself, I've got the value of a is equals to 3. Okay, this was 7, a is equals to 21, therefore a is equals to 3 directly. And again, in similar step, I can do this 2 steps in one itself. So within 2 steps, I'll get the answer. As it was, I was showing for the first time, and that is why I did this exhaustive steps. But once we get accustomed by this method, I can do the entire thing in 2 steps. So this is what I said, that it makes the thing condensed and compact. The method becomes condensed and compact within 2 steps. We got the answer. Second is it is sophisticated, which means till it were 2 variables, it was very easy to solve. The moment I change this equation and I write something like this, ax plus by plus c is equals to b1, say 5x plus 3y plus 2 is equals to 5. If I write something equation like this, so how many unknowns are there? 3 unknowns. So math says number of unknowns should be equal to number of equations. Then I will have to take 3 equations. Now if I write 3 equations, what you will have to do? First you will have to eliminate either x, y or z. Then you will get 2 equations. Then again that 2 equations you will have to solve. Then you will get one value. Then again that value you have to substitute, and the method will become very, very large. So at this moment, this method will be looking good, but the moment the number of unknowns increases, this method becomes very difficult. And if now I increase the unknowns to 4, then I will have 4 equations which I have to solve, which becomes very difficult. But if you have numbers over here, I can just simply add some, I can multiply row with anything, then I can add the rows, I can subtract the rows, I can divide the rows, all the operations I have shown in this particular thing. See here I have subtracted the rows, here I subtracted the rows, here I multiplied the row with some kind of number, then here also I had multiplied some row with the number, I added the rows in this case, I divided something with the number, therefore the method becomes very sophisticated and becomes very powerful. Even the number of unknowns, suppose the number of unknowns are 3, then the rows will become 3. Again, I can do the same procedure, it doesn't matter. Add 2 rows, subtract 2 rows, multiply with something, divide by something. If the number of unknowns are 4, then only the rows will become 4. Again, we can do the similar thing. So, what happens is it becomes very powerful. We cannot say that we'll stick to this method. Okay, if you just remember, or if you can ask your parents, the way you used to hold the pen when you held it for the first time, everyone would have done in this manner. So, is this the way you are writing today? No, you catch it like this. Why? Because initially, when you caught it like this, the hand must have pained. Initially, you must have thought, oh, it is very painful. My old method was right. But we know this provides more flexibility because of which you can draw any kind of pattern, you can write in any kind of pattern. It moves very quickly, therefore, you can write very fast as compared to this. Also, only this much portion of your hand moves, so less amount of the energy is wasted or in writing. But if you do like this, the entire hand movement goes. Hence, more energy is required to move and lift the hand. So you will be able to write only less. More amount of energy will get consumed, and that is why we had developed this kind of a technique to write. The similar thing applies over here also. Okay, initially it may look painful to us. Initially it may look, what are we doing? Why are we doing such kind of, you may find it a little bit complex, but as the time goes on, you will realize that this is very sophisticated and powerful too. Now, without even explaining any kind of properties, you yourself know what I have done was I had replicated the entire equation over here. I did not do anything which came to my mind. What I did is, whatever steps I did here, okay, I multiplied an equation, then I added the two equations when I solved by this method so that I can get the value of A and B. So the same thing I had done over here also. I did not do anything new. Whatever I had done over here, the entire same thing I have replicated over here, and therefore it must be now clear to you that if I'm writing just the numbers, okay, I can do anything, I can multiply, subtract, add, divide, anything. Okay, it doesn't matter. At the end of the day, the answer remains the same. If you just see here, I had got this answer last time A over here. And the next step when I did in the condensed step, I got the answer of A over here. But the answer remained same. A is equals to 3 I got here also, and here also I got A is equals to 3 only. Though I got answers in different rows and different methods, it doesn't, okay, it is not dependent on the method. You don't have to worry about anything in this particular thing, in this particular algebra called as matrices. And since it is using the linear equations, therefore this is also called as linear algebra. So it is very much clear to you. I multiplied it with 2, then I multiplied it with 6, then I divided it with 7, I added the 2 rows, I subtracted this 2 rows. Still, I ended up with the right answer which we had found over here. That is 3 and minus 1. So, it must be understood in your back of your mind that even you do anything, the final answer doesn't change. Since the final answer is not changing, you can do anything in the matrices, like adding 2 rows, subtract 2 rows, multiply anything with the row. And you must have also got it when we multiplied the equation number 1, when we multiplied it with 2, what did we do? We multiplied the entire equation, right? So we got 6A, 2B and 16. And here also when I did the same thing. Why? Because my first row was corresponding to the first equation. My second row was corresponding to the second equation. Hence, when we are multiplying, okay, in the matrices, you multiply either the entire row with the same number or you multiply the entire column with the same number. Okay, so little bit of idea you must have got. If you understood, then it's okay. If you did not understand, then also it's okay. Don't worry. It was just an introduction where I was trying to explain you from where these matrices have come. It has come from here only. We have developed the entire method of matrices from simultaneous equations which we have studied in the 10th standard. But since it is very powerful, we kept on adding the things in this algebra, and this algebra became very powerful. So now the algebra has become such a powerful that we don't only put the linear equations, we are even putting the values of quadratic equations, we are putting the vectors in the matrices, we are putting integrating things, which we are putting derivatives, and everything we are putting and we are solving. Okay, so let's start with this chapter now. This was just an introduction as of how and from where the matrices came. What is the fundamental from where the matrices have come, and if I'm adding, subtracting, multiplying, dividing, actually what am I doing? So whatever you have done to solve your linear equation, the same thing we are doing over here. So fundamentally it is similar. So starting formally the chapter now, this was only the introduction. If you have understood, it's okay. If you have not understood, then also it's fine. Now we are going to study the entire chapter in the detail. So I said, what will be the matrices will always be denoted with capital letters. Okay, matrices will always be denoted with capital letters. Similar we wrote for the set. Okay, why? Because I said the entire set of the numbers should be represented by something. So again, matrices is nothing but set of the numbers, and set is always represented by capital letters. Hence, matrix in singular form and matrices in plural form, it will always be represented with capital letters. Next, what we saw, there were some rows of numbers, there were some column of numbers. So matrices consist of rows and columns. Therefore, we have a notation something like this. A11. So whatever numbers we write inside a matrix is called as elements. Exactly same. Why? Because I said those set of numbers is represented by just the symbol in which we call it as matrices. So again, it is a set, and all the things which you write inside a set are called as elements. So here also, whatever we are writing in this square bracket, those will also be called as elements. And this element will shown by this symbol which I have written, something like this, A11. So what do we mean by A11? It indicates that the element is in the first row. So this one stands for the row, and the next one stands for the column. So we always write row first and then we write the column. So the next element I can write it as A12 because it is in the first row. This is my first column, this is my second column. So when I write A12, it represents the element is in the first row and the second column. So the next element can be written as A13, indicating that it is lies in the first row and in the third column. Similarly, I can write all the elements something like this. Similarly, the next element in the next row can be written as A21, indicating that it is in the second row, first column. And I can represent it as A22, indicating that it is in the second row, second column. A23, indicating that my element is in the second row and in the third column. Okay, similarly, I can write A31, A32, A33, and so on. So whatever number of rows, whatever number of columns are there. So I can write it something like this. So third row, first column, third row, second column, third row, third column. So we have assigned position for each and every element. If you look at it carefully, you'll understand what we have done is we have assigned a fixed position to each and every element in this matrices. So this is called as general representation. So this is called as general representation. So hence in general representation I can write that matrix, every element of matrix A can be represented something like this, Aij. This symbol stands for matrix and this all the elements I can represent something like this where I stands for row and J stands for column. So in general, I can represent any element of a matrix by this. I can write in the square bracket Aij. So when I write it in the square bracket Aij, it means it is an element of a matrix. If I write like this, then it is element of a set. If I write like this, then it is an element of a matrix. Okay, I stands for row, J stands for column. Similarly, it may be having certain number of rows and certain number of columns, right? So it is necessary to show how many numbers of rows are there and how many numbers of columns are there. So always I will show like this. So M over here stands for row, will always show row first and then will show column. So this is called as order of a matrix. So when we write rows and columns of a matrix, that how many number of rows are there, how many number of columns are there, then it is called as order of a matrix. Say for example, if I write A is equals to 1, 2, 3 and 4. Now how many rows are there? 1 and 2 rows are there. How many columns are there? 1 and 2 columns are there. So I'll write like this. So this is the order of the matrix and it is read as 2 by 2. Okay, it will be not read as 2 into 2. It will be read as 2 by 2. So this is the order of the matrix 2 by 2. If I write something like this, there is a matrix B and I am writing 1, 2, 3, 4, 5, 6, 7, 8, 9. So now how many rows are there? 1, 2 and 3. How many columns are there? 1, 2 and 3. So I'll write 3 by 2. So in this case, the order of the matrix is 3 by 2. Suppose I am writing one more or something like this 1, 2, 3, 4, 5, 6, 7, 8. So now how many rows are there? 2 rows. How many columns are there? 1, 2, 3 and 4. Okay. So rows will always be written first. Rows will always be written first and then you write the column. By convention. Okay, by convention you have to always write rows first and then you have to write columns. So there are 2 rows and there are 4 columns. So order of this matrix is how much? 2 by 4. So a matrix, okay, will always be defined with the order. Whenever we write a matrix, we should know what is the order of a matrix. Okay, so I hope it's clear to you guys. General representation and order of a matrix. Order of a matrix is nothing but number of rows, number of columns. And it is read as by and not into. So 2 by 2, 2 by 3, 3 by 3, 2 by 4, something like this. Okay, next we'll see types of matrices. There are many types of matrices. I am only going to show those matrices which are there in your syllabus. Okay, again when you enter into engineering in your first year itself, okay, when you enter, you are going to get M1, and in the next semester you are going to get M2, where again you are going to come with the same chapter matrices. Again, there you are going to study much more types of matrices. The very first, row matrix. So what is the row matrix? It has only single row. It can have n number of columns, but it can have only one row. Such a matrix will be called as a row matrix. Say for example like this, 1, 2, 3. Only one row is there, 3 columns are there. Or I can write matrix B something like this, 1, 2, 3, 4, 5. So the number of columns are 5, but row is only 1. So such a matrix is called as a row matrix. Then you have one more which is called as column matrix. So it is going to have single column. It can have n number of rows, but it will have only one column. Then it is called as a column matrix. Say for example, 1, 2, 3. There is one more matrix B. Okay, having elements A, B, C, D. In this case, there are 3 rows, and here there are 4 rows. But the number of columns are only 1. So, if the number of columns is only 1, then it is called as the column matrix. Okay. Third type of matrix is a square matrix. So if you know what is a square, if all the sides are equal, then it is called as a square. So here in this case, if the number of rows are equal to number of columns, then it will be called as a square matrix. The number of rows will be equal to number of columns. So when number of rows are equal to number of columns, then the matrix is called as a square matrix. Say for example something like this, 1, 2, 3, 4. So 2 rows are there, 2 columns are there. So this is a square matrix. Say for example, so number of rows are also 3 and number of columns are also 3. So a square matrix will always be like having the order 1 by 1, 2 by 2, 3 by 3, 4 by 4, 5 by 5, 6 by 6, and so on, where number of rows are equals to number of columns. Then the matrix is called as a square matrix. Now, most of the calculations or most of the linear algebra, whatever we have for the matrix, okay, the maximum amount of the algebra, okay, for a matrix is applied on square matrix only. Okay, it's not that it should always be a square matrix only, but the maximum amount of algebra which we are going to study in this linear algebra, or also called as matrix, is applied on this type called as square matrix. So now whatever types I'm going to write, all those types will be nothing but all are going to be subtypes of square matrix. So the very first subtype of a square matrix is upper triangular matrix. Okay, so before going to that, if there is a square or rectangle or anything, it is going to have two diagonals, right? This will be my one diagonal and this will be my another diagonal. So if it is a square or a rectangle or a parallelogram, any quadrilateral is going to have these two diagonals. Similarly, here also we are going to have two diagonals. This will be one diagonal, okay, and this will be another diagonal. So here also we are going to have two diagonals. Out of these two diagonals, one diagonal will be called as principal diagonal. So in this case, the yellow colored one will be called as principal diagonal. Okay, the yellow colored one which I have done over there is called as principal diagonal. Now, why do we call it as principal diagonal? So if you take all the elements of this yellow color, so this will be A11, this will be A22. If you take over here, so this will be A11, this element will be A22, this element will be A33. Okay, so it exactly matches with the definition of square matrices where number of rows is equals to number of columns. So the element in each element of this diagonal will go with the similar property. This will be A11, this will be A22, this will be A33. Hence, the yellow colored diagonal will be called as the principal diagonal. So all the other definitions, whatever, are going to be based on this principal diagonal. So when we say the word diagonal of a matrix, it always refers to principal diagonal. Okay, even if this word principal diagonal is not used, okay, it should be beared in the mind that whenever the word diagonal is used, it always refers to principal diagonal. So now what is upper triangular matrix? If elements below the principal diagonal are all zero. Let me give you an example. If I write a matrix C, so if you can see here, this is my principal diagonal and the numbers below the principal diagonal are all zero and the numbers above the principal diagonal are non-zero. So if it's not that it should be all the numbers should be non-zero. If I write 0 over here and if I write 0 over here, then also it's fine. At least there should be one number which is non-zero, okay, above the diagonal. There should be at least one number which should be non-zero above the diagonal. So in this case, if you see, the numbers above the diagonal are non-zero and all the numbers below the diagonal are zero. So if the elements below the diagonal are zero, okay, all are zero, then it will be called as upper triangular matrix. Triangle. So you can see clearly, you can see here I have made a triangle. So the elements in this triangles are non-zero and therefore it will be called as upper triangular matrix. So similarly we have lower triangular matrix. So again it is a square matrix. Okay, all these are subtypes of square matrix. So square matrix where elements above the diagonal are zeros. So if the elements above the diagonals are zeros, then it will be called as lower triangular matrix. So this is my principal diagonal, okay, and this is my elements above the diagonal and these are my elements below the diagonal. So I have made two triangles. In one triangle all the elements are zero and other triangles the elements are non-zero. Okay. So if above the diagonal then zeros are there, then it will be called as lower triangular matrix. And if below the triangle all the elements are zero, above the diagonal if the elements are zero, it is called as upper triangular matrix. Or if you are having confusion, you can remember it as upper triangular matrix is where elements above diagonal are non-zero. Therefore, upper. Elements, okay, lower to the diagonals are non-zero. Therefore, lower triangular matrix. So, whichever way you can remember, in that way you can remember it. Okay, next type of matrix is called as diagonal matrix. So, what is the diagonal matrix? So, only elements of diagonal are non-zero, all the other elements are zero. So, elements above and below the diagonal are zero. Okay, let me write one more matrix, something like this: 1, 2, 3, 0, 0, 0, 0, 0, 0. So, you can see over here, this is my diagonal. The elements above the diagonal are also 0 and the elements below the diagonal are also 0. Okay, elements above the diagonal are also 0, elements below the diagonal are also 0. Okay, then the matrix is called as a diagonal matrix. All these are square matrix: upper triangular matrix, lower triangular matrix, diagonal matrix. All these are nothing but square matrix only. Next type of matrix is called as identity or unitary matrix. It is always denoted by letter I. Identity matrix or unitary matrix means unit matrix. Okay, or it is many times also called as unit matrix or unitary matrix or identity matrix. So unit means what? One. So it is something like this. So in a square matrix, if all the elements above the diagonal are 0, below the diagonal are also 0, and all the elements of the diagonals are 1. You can see here, this is same as the diagonal matrix. You can see that unitary matrix is also a diagonal matrix where all the elements of the diagonal are 1. So if all the elements of a diagonal matrix are 1, then that diagonal matrix will be called as unit matrix. You can see it. Okay, all the elements above and all the elements below the diagonal are 0 and all the elements of the diagonal are 1. Okay, then such a matrix is called as unit matrix or identity matrix, and this identity matrix will always be denoted by I. So now how many rows and columns are there? 3 rows and columns. So I can also write it as I3. So I can also write something as I2. So when I write I2, so we know it is a square matrix. So it should have 2 rows and 2 columns. So 1, 0, 0, 1. So this is my diagonal. Okay, elements above the diagonal, below the diagonal are 0. Elements above the diagonal and elements below the diagonal are 0. And it is 2 by 2 matrix. So I can also write it as I2. So many times we will write equations in matrices, and there we may use the suffix such as I3, I2. So you should not get confused. So when I write I3, it is identity matrix where the order is of 3 by 3. If I write I2, again it is an identity matrix where the order is of 2 by 2. Okay, now before going to the next type of matrix, I will show you an operation, and after that we'll go to the next type of matrix. Okay, and this operation is called as transpose of a matrix. So it is denoted by A dash, or it is denoted by A raised to T. Okay, you can denote it by A dash, or you can denote it by A raised to T. Okay, so transpose. So what do I mean by transpose? It simply means interchange rows with columns, or vice versa. So transpose of a matrix, what does it mean? You have to interchange rows with the columns. So suppose I have a matrix something like this. 1, 2, 3, 4, 5, 6, 7, 8, 9. So my row is 1, 2, 3, my second row is 4, 5, 6, my third row is 7, 8, 9. Okay. Then when I say interchange rows with columns or A transpose, so it is denoted by A raised to T, or you also write it as A dash. So what does the transpose mean? Interchange rows with columns. So this row 1, 2, 3 will become column. These row 4, 5, 6 will become a column 4, 5, 6. These row 7, 8, 9 will become a row 7, 8, 9. Is this clear to everyone? This transpose. Okay, write all the rows as columns as it is. As simple as that. Very simple. Whatever rows are there, just write the rows as columns. So now, if you have understood what do I mean by transpose of a matrix, we are going to see special type of matrix called as symmetric matrix. So we know in symmetric means mirror images. So if the matrix is the mirror image of each other, okay, or about a diagonal, then it will be called as a symmetric matrix. Or we give an algebraic condition to it. If my A transpose is equals to A. So if I interchange the rows with columns, and if I end up with the same matrix, what I do is I do transpose, and after doing transpose, I'm still getting the same matrix. Okay, after doing transpose also, and if I'm getting the same matrix, then it will be called as symmetric matrix. So let's see an example. You will understand. Let me take a matrix something like this. Okay, so I've written some matrix something like this. And now let me take transpose of this matrix. Now this is my row 1, 2, 3. I'm writing it as a column 1, 2, 3. Then I'm taking this row 2, 4, 5 and I'm writing as a column 2, 4, 5. Then I'm taking this row 3, 5, 6 and I'm writing it as a column 3, 5, 6. Is this two matrices exactly same? Just see and tell me. C matrix A and C matrix A dash. Is it exactly the same matrix? See and tell me, is it exactly the same matrix? Yes or no?
Yes, sir.
It's exactly the same matrix. Okay. Though I've done transpose, I've written this row as the column, I've written this row as the column, and I've written this row also as the column. And if you observe, the matrix is exactly same. My matrix A and my matrix A dash is exactly same. So it is matching this definition. So from here I can say my A is equals to A dash. So if my A is equal to A dash, then matrix A is called as symmetric matrix. So if my A transpose is equal to A, then my matrix is called as a symmetric matrix. Therefore, this given matrix A, this given matrix A will be called as symmetric matrix. Okay? Is it clear? I hope it's clear. Now let's see next type of matrix. Let's see next type of matrix. Q-symmetric matrix. If my A transpose is equals to minus A. If my A transpose is equal to minus A, then the matrix is called as Q-symmetric matrix. Let us try to see with an example. So this is my matrix A, okay, and now let me take transpose. So when I do transpose, what I'll do, I'll write this row as column. So this row is 1 by 6. I will write it as a column. Then next row minus 5 to 7. So I'll write minus 5 to 7 as a column. Then next row minus 6 minus 7 4. So minus 6 minus 7 4. I'll write it as a okay, I'll write it as a column. Now if you see, okay, this negative have come over here. So if I multiply this matrix with okay minus, then I'll get this entire this matrix. So in such a scenario, this matrix A, okay, will be called as skew symmetric matrix. So when I get A transpose is equal to minus A, okay, then I can say that the given matrix is skew symmetric matrix. Okay, then the given matrix is nothing but skew symmetric matrix. Is this clear? Clear what is symmetric matrix, what is skew symmetric matrix?
Yes, sir.
One more thing, equality of matrices. When can I say that two matrices are equal? So suppose I have one matrix, say 1, 2, 3, 4. I have another matrix 1, 2, 3, 4. I have one more matrix 1, 2, 3, 4. So which matrix am I going to say equal? Can I say matrix A and matrix B are equal? Can I say matrix B and matrix C are equal? Or can I say matrix A and matrix C is equal? Which one is correct? Or all the three are equal? You see, all the three matrices have same element 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. But if you see, the position of the numbers are not same. If you check, okay, matrix A and matrix B, the positions are not same. Your position is same, but here the position of 3 and here the position of 3 is not same. Here I have 3 at the position A to 1 and here I have at the position A to 2. Similarly, the position of this 4. Here my 4 is at the position A to 2, whereas here the position is A1 2. So I'll not say that both these matrices are equal. matrix A is not equal to matrix B. But if you consider A and C, okay, all the elements and their corresponding position are also same. Therefore, I'll say my matrix A is equal to matrix C. So, what do we understand from this? If only elements should not be same. Elements and their corresponding position, or in very short, you can say if the corresponding elements of two matrices are same, then the two matrices are said to be equal. The two matrices are said to be equal if and only if their elements and their corresponding positions are same. In other words, if the corresponding elements are same, then only a matrix is called, the two matrices will be said to be equal. Otherwise, the two matrices are not equal. You can clearly see over here. I've taken all the three matrices having the same elements, but the corresponding elements are not same. Since the corresponding elements are not same, therefore these matrices are unequal matrices. Is it clear? When can we say two matrices to be equal? Clear? Okay. So next we are going to study operation on the matrices. So whenever we study new type of algebra, we'll always do the four basic operations in mathematics. What are they? Addition, subtraction, multiplication, and division. So whenever we develop new kind of an algebra, or whenever we learn new type of an algebra, we always have to check, or we always have to learn these things: adding, subtracting, multiplying, and division. So in complex numbers also you must have learned how to add the complex numbers, how to subtract, how to multiply, and how to divide. Okay. In vectors also we'll study how to add two vectors, how to subtract, how to multiply, and how to divide the vectors. Same is here also. How to add two matrices, how to subtract two matrices, and how to divide two or multiply two matrices. So I have a matrix A and I have one more matrix B. Now I want to add two matrices. So if you remember in the beginning when I started with the introduction, each column corresponded to a particular quantity. So this entire is going to correspond to A, this entire is getting correspond to B. So A will be added with A elements only and B will be added with B elements only. So it is as simple as that. Addition or subtraction will always be done with corresponding elements. So A11 of this will get added or subtracted with A11 of this. Okay, A21 will get added or subtracted with A21. A22 will get added or subtracted with A22 and so on. So in addition or subtraction, what will we do? We will add or subtract corresponding elements. So addition or subtraction will always be done for the corresponding elements. So when I add over here, this and this are corresponding, so I'll do 1 plus 5. This and this are two corresponding, so this 2 will get added. This 3 and this 7 are corresponding numbers, so I'll add both the numbers. Similarly, 4 and 8 are corresponding numbers, so I'll add both the numbers. So I'll get 6, 8, 10 and 12. If I do B plus A, which means I will have to write B matrix first, 5, 6, 7, 8, and then I have to write A matrix 1, 2, 3, 4. So let's see what is the value of B plus A. So 5 plus 1, that will be 6, 6 plus 2, that will be 8, 7 plus 3, that will be 10, 8 plus 4, that will be 12. So if you see this and if you see this, it is exactly same, and therefore I can say that my A plus B is equals to B plus A, which means addition of matrices is commutative. Okay, we have commutative law, distributive law, and associative law. So what we have just proved is that addition of two matrices is commutative. Let's see subtraction. So if I do A minus B, I'll have to write matrix A first and matrix B next. So matrix A 1, 2, 3, 4 minus B. So next I'll write matrix B 5, 6, 7, 8. So A minus B will be, you have to subtract corresponding elements. So 1 minus 5 minus 4, 2 minus 6 minus 4, 3 minus 7 minus 4, 4 minus 8 minus 4. Okay, now let's see B minus A. So when I do B minus A, I will have to write matrix B first. 5, 6, 7, 8 minus A, matrix A 1, 2, 3, 4. So I'll get B minus A as 5 minus 1, 4, 6 minus 2, 4, 7 minus 3, 4, 8 minus 4, 4. And here I am getting all the elements as negative, here I am getting all the elements as positive, and therefore A minus B is not equal to B minus A. Therefore, subtraction of the two matrices is non-commutative. Addition of two matrices is commutative, whereas subtraction of two matrices is non-commutative. Okay, I hope it's clear to you. Commutative and non-commutative. Let's also check for associative or distributive properties. So how do you write associative? A plus B plus C will be equal to A plus B plus C. So this is called as associative law. So let's prove associative law. Let us take one more matrix. Okay, so let's do A plus B plus C. Here I have given bracket to B plus C. So first I will have to add B plus C, and in that matrices I will have to add A. When I do B plus C, corresponding elements will get added 5 plus 2. So that will be 7. 6 plus 1. That will be 7. 7 minus 1. That will be 6. 8 plus 4. That will be 12. So this is value of B plus C. In this B plus C, I have to add, this is my LHS, I have to add A. In which matrix? In matrix B plus C. Okay, so 1 plus 7, that will be 8, 2 plus 7, that will be 10, 3 plus 6, that will be 9, 4 plus 12, that will be 16. So this is my value of my LHS, which is A plus of B plus C. Now here I have given the bracket to A plus B, which means first I will have to add A plus B. And in that I will add my matrix. So let's do A plus B, 1 plus 5, 6, 2 plus 6, 8, 3 plus 7, 10, 4 plus 8, 12. And in this I will have to add C. So I'll add C over here, that is 2, 1 minus 1, 4. So I'll get A plus B plus C as 6 plus 2, that is 8, 8 plus 1, that is 9, 10 minus 1, that is 9, 12 plus 4, that is 16. So see, is it same? Did we do any mistake? plus c 5 plus 2 7 6 plus 1 7 7 minus 1 6 8 plus 4 12 7 plus 1 8 7 plus 2 sorry 9 plus 7 plus 2 is 9. So now you can see my LHS is 8 9 9 16. My RHS that is also 8 9 9 16. And therefore I can say addition of matrices is associative. Same you can prove for distributive also. I'm not going to prove all those things. Now we'll move ahead with the next type of operation. So we have seen how to add two matrices and how to subtract two matrices. If you're not understanding at any point, or if you think that sir is going very fast, then please let me know. If at any moment you think that sir is going very fast but you are not understanding, then please let me know. Okay, let's see the next operation, which is called as scalar multiplication. So all these things I have shown you in the beginning of the lecture also today. So the scalar multiplication with any number or a constant is called as scalar multiplication. Multiplying a matrix, okay, with a number or with a constant is called as scalar multiplication. Say for example, I have this matrix 1, 2, 3, 4. So if I am writing 3A, what does it mean? It means 3 times the matrix A. So I write 3 and I write here matrix. So what does it mean? All the elements of the matrix A will get multiplied by 3. So 3 into 1 that will be 3, 3 into 2 that is 6, 3 into 3 that is 9, 3 into 4 that is 12. So the value of 3A will be 3, 6, 9, 12. Okay. Suppose I say BA. It means I'll multiply the entire matrix A with B. That is 1, 2, 3, 4. So what I'll get? 1 into B, that is B. So this will be 2B, this will be 3B, this will be 4B. So this is what I mean by scalar multiplication. So whenever you write any number or a constant with the matrix, the entire matrix gets multiplied by that particular number, then it is called as scalar multiplication. Okay, suppose if I write minus 2A, it means I'll multiply the entire matrix A with minus 2. That is 1, 2, 3, 4. So when I multiply, I will get minus 2, minus 4, minus 6, minus 8. Okay, so this is scalar multiplication. I hope you have understood what is scalar multiplication. Let's see one or two simple problems. Suppose I have one matrix A as 1, 2, 3, 4. I have another matrix B as 2, minus 1, 1, minus 3. Okay, and if I am writing, find the value of 3A plus 2B. I want to find out the value of 3A plus 2B. It means I have to multiply the entire matrix A with 3, then I have to multiply the entire matrix B with 2, and then I have to add both the matrices. So my matrix 3A will be nothing but 1, 6, 9 and 12. And my matrix B will be 4, minus 2, 2, minus 6. So my 3A plus 2B will be nothing but add both these matrices. So 1 plus 4 that will be 5, 6 minus 2 that will be 4, 9 plus 2 that will be 11, 12 minus 6 that will be 6. So the value of 3A plus 2B will be this. Similarly, if I write 3A minus 2B, So then it will be nothing but you will have to subtract these two matrices. So 1 minus 4, that will be minus 3. Oh, sorry. Sorry, I made a mistake. 1 into 3, that will be 3. So 3 plus 4, that will be 7. Sorry, I did mistake. So now here I'll do 3 minus 4. So that will be minus 1. 6 minus, this is minus 2. So 6 minus minus 2. So that will become 6 plus 2. So that will become 8. Similarly, 9 minus 2, 7, 12 minus minus 6. So that will become 12 plus 6. So this is the value of 3a minus 2b. Is it clear? Is it clear to everyone? Any doubts in whatever we did up till now? Okay. If no doubt, then let's move ahead and let's see how to multiply two matrices. Understand this procedure very properly. And at any moment, if you're not understanding anything, then please let me know. Okay, now before going to this, we saw addition and subtraction of two matrices. One more important point I forgot to highlight is that two matrices can be added or subtracted if and only if their order is same. Suppose I have a matrix something like this. Matrix A is 1, 2, 3, 4. And I have a matrix 1, 3, 5, 7, 8, 9. Now can I add these two matrices? Not possible. Because here the order of matrices is 2 by 2, whereas here the order of the matrix is 2 rows, 3 columns, 2 by 3. How to add two matrices or subtract two matrices? Okay, addition or subtraction is done with corresponding elements, right? But if you don't have corresponding elements, you have corresponding elements for this over here. But what about this? You don't have any elements corresponding to 5 and 9. And you cannot assume that, sir, if there are no elements, consider it as 0. How come? If you want to consider 0, I can consider any number. I can consider any negative numbers. I can consider any positive numbers in place of that. So, it becomes ambiguous. So, different people will get different answers. And therefore, two matrices cannot be added if their orders are not same. Okay, here the order is 2 by 3, here the order is, and very important result, two matrices can be added or subtracted if and only if their order is same. Okay, if their order is different, then addition is not possible, subtraction is not possible. But when we talk about multiplication, it may or may not be possible. So let's see multiplication of matrices. So in addition, we had a condition that okay, two matrices can be added or subtracted if and only if their orders are same. Here the condition is not that. Here the condition is, and it is very important, column of first matrix should be equals to rows of second matrix. Very, very important. So suppose I have a matrix A having order 3 by 2 and I have a matrix B having an order 2 by 4, then multiplication of these two matrices is possible if the number of columns of first is equal to the number of rows of second matrix. Okay, and what will be the order of the matrix, resultant matrix? It will be this. So the multiplication is possible and the matrix which I get as multiplication of A and B will have an order of 3 by 4. Okay, 3 rows and 4 columns. But suppose I write the opposite. If I write B first and then I write A. So order of B is 2 by 4 and order of A is 3 by 2. So here the number of columns is 4 and here the number of rows is 3, which is not equal. Therefore, this multiplication is not possible. So see, very important thing over here. In addition and subtraction, we had a condition that number of rows should be equal to number of columns. But in multiplication, we don't have any such condition. But one condition we have is column of my first matrix should be equal to row of the second. So when I did A and B, so A became my first matrix, B became my second matrix. So I have to check column of the first matrix with the row of the second matrix. And both were exactly same, therefore multiplication was possible and the resulting matrices would have been of the order 3 by 4. But when I did the opposite of that, that is I wrote B first and then I wrote A first, then what happened? We have to see column of the first. So column of the first is 4 with the rows of the second. The rows of the second is 3 and it should be equal, but it is unequal. One is 4 and other is 3. Therefore, the multiplication is not possible. So forget about AB is equals to BA. In matrices, I've just shown you a condition where AB is possible and BA is not possible. Forget about even being commutative. If it is commutative, then my AB will be equals to BA. But in this case, forget about commutative. In many cases, it may be that multiplication itself does not exist. Are you getting it? So when is multiplication possible? Very important. It is possible if and only if the column of the first matrix is equal to row of the second matrix. Is it clear? Is it clear? And if it is a square matrix, you don't have to worry anyways. If it is a square matrix, you don't have to worry anyways. Okay? For square matrix, it will be possible. If the order of the square matrix is the same. If the order of two square matrices is the same, then AB will also exist and BA will also exist and the resulting matrix will have, that will also be a square matrix of same order. See, for example, I take a matrix whose order is 3 by 3 and I take another matrix whose order is 3 by 3. Now first, number of columns of first matrix should be equal to number of columns of the second matrix. Yes, done. And the order of the matrix will be this. So AB will exist and I'll get the order of the AB matrix as 3 by 3. And if I do BA also, then also I don't have to worry. BA is also of 3 by 3. A is also of the matrix 3 by 3. Number of columns of first is equal to number of columns of second. And the resulting will have an order of this. So BA also exists. and will have the same order as 3 by 3. So if there are two square matrices whose order is same, then both AB will also be exist and BA will also exist. You don't have to worry about that. But the value of AB may not be equals to value of BA. Okay, the value of AB may not be equals to BA, but if square matrices having same order, then my AB and BA both exist. Without even a doubt, you don't even have to worry about okay it exists or not. You can directly start multiplying A with B, you can directly start multiplying B with A. So till here is it clear? Let's learn how to multiply two matrices. So the multiplication is done. Rows of first matrix are multiplied and added with the columns of second matrix. So whichever matrix you write first, you have to consider rows of that matrix which will multiply with the columns of the second matrix. So let's see how to do it. Let's learn how to multiply two matrices. I take a matrix A, 1, 2, 3, 4, and I take a matrix B, 1, 2, 2, 3, and I'm writing A into B. So I'll write this A as 1, 2, 3, 4, and then I'll write matrix B 1, 2, 2, 3, and then rows of first and columns of second. So you can also remember something like this. These arrows are very important. Okay, we'll go from left to right, and here we will go down the column. Here in the rows will go from left to right, and the column will go from up and down. So how will multiply 1 into 1 plus 2 into 2. So first row, first column is done. Then you will multiply first row with second column. Okay, first row with first column, first row with second column. So 1 into 2 plus 2 into 3. Okay. Similarly, second row into first column, second row into second column. Okay, what we did, first row into first column, first row into second column. Similarly, second row into first column, second row into second column. These arrows you have to remember. So this with this 3 into 1 plus 4 into 2. So first element of this with first element of this, second element of this with the second element of this. So how will you decide which is the first and second element? That is why I have given this arrowheads. Okay. So if I go down the line, this will become my first, this will become my second. If I go left to right, this will become my first, this will become my second. So first row into first column, first row into second column. So 3 into 2 plus 3 into 3. So I'll get AB is equal to 1 into 1 is 1, 1 plus 4 that is 5, 2 plus 6 that is 8, 3 plus 8 that is 11, 6 plus 9 that is 15. So this is the value of AB. Everyone has understood the procedure. Everyone has understood the procedure. Let's see one more. Let me find out the value of BA. So when I write BA, I'll write matrix B first and then I'll write matrix A. So B matrix I'll write first 1, 2, 2, 3. And then I'll write matrix A, that is 1, 2, 3, 4. So again the procedure will be same. First row into first column, then first row into second column. Then second row into first column, second row into second column. Okay. So I'll get BA is equals to 1 into 1 plus 2 into 3. Then first row into second column, so 1 into 2 plus 2 into 4. Then second row into first column, second row into second column. So second row into first column, so 2 into 1 plus 3 into 3. Then second row into second column, so 2 into 2 plus 3 into 4. So I'll get the value of BA as 1 into 1 plus 6, so that will be 7. 2 plus 8, that will be 10. 2 plus 9, that will be 11. 4 plus 12, that will be 16. So see, the value of AB and the value of BA is different. Therefore, my AB is not equals to BA. Thus, I can say that multiplication of two matrices is non-commutative. Multiplication of two matrices is non-commutative. Multiplication of numbers is commutative. That is, if you do 5 into 2 or you do 2 into 5, the result will be same. Multiplication of numbers is commutative, but the multiplication of matrices is non-commutative. I have clearly shown you here, this is my value of AB, this is my value of BA, and the matrices is not same. Therefore, multiplication of matrices is non-commutative. Let us see once more. This time we'll increase the number of rows and columns. Let me take one more example. I have a matrix A, 1, 2, 3, 4, 5, 6, 2, 1, 2. I have a matrix B, 1, 2, 1, 2, 1, 3. So I have these two matrices, matrix A and B, but this time what I have done is I have increased the order. So the calculation will also increase first row into first column, first row into second column, first row into third column. Similarly, second row into first column, second row into second column, second row into third column. Similarly, third row into first column, third row into second column, third row into third column. So let's solve this. Let's find out the value of EB. So we'll write matrix A first and then we'll write matrix B. So first row into first column, so 1 into 1 plus 2 into 2 plus 3 into 4. Okay. Then first row into second column. So 1 into 2 plus 2 into 1 plus 3 into 1. Then first row into third column. So 1 into 1 plus 2 into 3 plus 3 into 2. Then second row into first column, second row into second column, second row into third column. So second row into first column, so 4 into 1 plus 5 into 2 plus 6 into 4. Then 4 into 2 plus 5 into 1 plus 6 into 1. Then second row into third column, so 4 into 1 plus 5 into 3 plus 6 into 2. Okay. Then third row into first column, third into second column, third into third column. So 2 into 1 plus 1 into 2 plus 2 into 4. Similarly, 2 into 2 plus 1 into 1 plus 2 into 1. Then 2 into 1 plus 1 into 3 plus 2 into 2. So we will get the final answer. So that will be 1 plus 4, 5, 5 plus 12. Okay, 17, 2 plus 2, 4, 4 plus 3, 7, 1 plus 6, 7, 7 plus 6, 13, 4 plus this 10, 14 plus 24. So 38. 8 plus 5, 13, 13 plus 6, 19. 4 plus 15, 19, and 19 plus 12, 29. 2 plus 2, 4, 4 plus 8, 12. 2 plus 1, 4 plus 1, 5, 5 plus 2, 7. 2 plus 3, 5, 5 plus 4, 9. So this is the value of my AB. So have you understood this multiplication? This time I have done a bigger multiplication. I have multiplied 3 by 3 matrices, and again I have got a matrix of order 3 by 3. Is it clear? Okay. So suppose now I do something like this. Now, is the multiplication possible? Here the order is 3 by 3 and here the order is 3 by 2. So number of columns of first should be equal to number of rows of second. It's there. Therefore, my resultant matrix will have order 3 by 2. Okay. So this will go and I'll get this. The resulting matrix will have the order 3 by 2. So yes, it is having the order 3 by 2. The number of rows are 3 and the number of columns is 2. So now I have done this time a multiplication of two matrices whereas the order is not changed. One matrix is of order 3 by 3, other matrix is of order 3 by 2. In that case, again the multiplication will remain same, row into column, row into column. So now you must have understood that suppose I eliminate this column. Then for these two numbers we have 3 will get multiplied by which number? And therefore the multiplication is not possible if number of columns of first is not equal to the number of rows of second. So what I had written over here was 1 and here it was 2. So it's clear the multiplication. So here is the multiplication when the order is not same, which means if the matrices are not square matrices, then also we can multiply and we can get this answer. Clear? So now we know how to add the matrices, we know how to subtract two matrices, we know how to multiply the matrices, and we also know scalar multiplication of a matrix. So now as we know all these things, okay, we can start solving some numericals. Okay, so let's do some numericals. So I have a matrix A. I have this matrix. And I want to find out the value of come on. If you have understood, solve this and tell me the answer. Okay, find out the value of 2ab plus 3ba and tell me what is the answer. Solve this and tell me what is the answer of this equation. 2ab plus 3ba. ये कौन सा लेक्चर चल रहा है? Are you guys solving? What is the answer? I told you guys to solve. Let me see any answers. Okay, you guys can cross verify the answer. So first let us find out the value of AB. So first go into first column. So 1 into 2 plus 2 into 3. Then first go into second column. 1 into minus 1 plus 2 into 4. Then second go into first column. 3 into 2 plus 4 into 3. Then second row into second column. 3 into minus 1 plus 4 into 4. So I'll get the value of AB as 2 plus 6, that is 8, minus 1 plus 8, that is 7, 6 plus 12, that is 18, minus 3 plus 16, that is 13. Let's find out the value of BA. So first row into first column. So 2 into 1 plus minus 1 into 3. Then first row into second column, 2 into 2 plus minus 1 into 4. Then second row into first column, 3 into 1 plus 4 into 3. Then second row into second column, 3 into 2 plus 4 into 4. So you will get VA is equals to 2 minus 3 minus 1, 3 plus 12. So that will be 15, 4 minus 4. That will be 0, 6 plus 16. That will be 22. So now 2AB. So 2AB will be equal to 8 into 2, that is 16, 7 into 2, that is 14, 18 into 2, that is 36, 13 into 2, that is 26. 3BA. 3BA will be equals to minus 3 minus, sorry, plus 45, 0 and 66. Now I need to do 2AB plus 3BA. So I will have to add these both matrices. So 2AB plus 3BA will be equal to 16 minus 3. So that will be 13. 14 plus 45, 9, 59. 36 plus 0, that will be 36. 26 plus 62, that will be 92. Okay, so this is the value of my 2AB plus 3BA. Is it clear? I hope you have to multiply and all those things. So in the next lecture, we'll directly start with the numericals. Okay, if you have any doubt or any problems, you can okay, always reply in the group. I'll always reply there. Okay, if you have any problems. Very good. Okay. So today you have understood whatever we have done. So we'll directly start with the numericals. Okay, before the numericals, we'll write certain properties. Matrices cannot be solved without certain properties. So we are going to write a lot of properties. So one more lecture will go on the properties. There are properties of square matrices. There are properties of diagonal matrices. There are some properties of then we'll see inverse of a matrix. And there are properties of adjoint of matrices. Lot of properties are there. We have to see, we have to buy out those properties, and then we'll start with the GW numericals. Okay. Have a nice day ahead.
Thank you, sir.
Welcome.